Hello, everyone. So in the meanwhile, while we're waiting for people to join, could you just pop your year group in the chat function, just so I know and have an idea of who's here today? Okay, so we've got year 10, excellent. Great, okay, we've got year 10, year 11. I'll just wait 1 minute for everyone to join and then we'll start in just a bit. What year group is everyone else from? Okay, I think I'll wait till 3 minutes past and then we'll get started. Guys, we've got a couple of responses, but what year group are you all from? We've got some year 10s, some year 11s. Okay, we got some more year 10s, year 9, fantastic. And we're nearly ready to get started. I'm just waiting till 3 minutes past and okay, right. So hopefully anyone coming in will just be able to pick it up as they go along. Let's get started with our presentation. So again, today we're going to be focusing on GCSE Physics. And just to introduce myself a little bit, hi, my name is Darina. I studied chemistry with molecular physics at Imperial College London University. And I'm obviously going to be giving the presentation today. So what we're going to focus on today. So this is a series about electricity. And today, specifically, we're going to be focusing on domestic uses and safety, and then doing a little bit on static electricity, because that is also very important when considering, the potential uses for it, but also the safety aspects of it. So let's start off with mains, electricity, and domestic uses. So just to start the presentation, I've got a bit of a question. Now, you don't have to answer this straight away, but just to think about them. So we'll be discussing some aspects and then coming back to them later on in the lecture. So firstly, what is mains electricity and how does it get to our homes? And secondly, what safety measures are used with mains electricity? So that's what we're going to be talking about in the first part of the lecture. So firstly, starting with what is mains electricity and how does it get to our homes? Anyone got any ideas just to start off? How does mains electricity get to our house? So if you could just pop any ideas that you have in the chat. All right, we've got a few ideas, great. So people mentioning cables, how transformers work. Yeah, so we have a system called a national grid, which takes electricity from whatever generators that we have and takes them to our houses. But firstly, we have to generate that electricity somewhere, right? So where we start at is at power stations. So these look roughly like this, kind of grim, but this is where electricity is generated. And then when they are transmitted to your houses, they, as some of the answers were saying, you use a system of cables and transformers. We're not going to go to transformers today because that's a little bit on the magnetism side, but they're basically just used to prevent energy loss in wires. Right, so let's have a little closer look at power stations and how they work. So this is just a little bit of a diagram. So we basically have some kind of energy source, such as burning coal or something like that, which heats up water. and this turns a turbine, which is linked to a generator, and this produces electricity for us. So have a little look at that diagram, and can anyone think, why are power stations built near the sea or large lakes and rivers? Going off that image that I've got on the right there. Don't be shy, just put any answers that you know, anything that you think of in the chat, and we'll talk about it. Right, does anyone have any ideas why why most power stations are built near the sea or near large lakes? What do you think we need a lot of in this system? All right, we've got some answers. So one person's commented on that when there's loads and loads of demand for electricity, you know, some things don't work, such as a kettle. That is correct. So usually power stations try and regulate how much electricity they send, but sometimes when there is an especially high demand, something that requires a lot of power, such as a kettle, just doesn't work. So yes, that is a true story. We've got a couple of answers about the question that I asked, which is, well done, you guys. You've got, because they need large bodies of water, and the reason that they need large bodies of water is for this cooling and heating system, right? So we see that steam is produced, and the reason why that's produced is that is what actually turns the turbines and is heated up using the fuel. So we heat the water up using the boiler, it then turns some kind of turbine and then is released into the atmosphere. But for all of this to work, they need access to large bodies of water. So yes, well done, everyone. You've got that in the chat. All right. Now let's have a look in what form Oh, we've just got a little question in the chat here. And by the way, if you've got questions, please don't use the Q&A function. Please just put them in the chat. Okay, so there's a question. Is there any other way to turn turbine other than water or wind? So most power stations work on the principle of we have some kind of source of energy which heats up water, that turns into steam, rises up a particular column, that turns the turbine and therefore generates electricity. And when you get onto electromagnetism, you realize why we need that turning effect for the generator to work. There are loads of ways to generate electricity. There is geothermal energy, there is solar energy. So it's not the only way, but it is the way that we would look at most at GCSE. So that's kind of the model that we're running with right now. All right, and then let's have a little look at how this electricity looks like when it reaches our houses. So the model that we have so there are two forms of current, and we mentioned this in our first lecture last week, right? And can anyone tell me what the two types of current are and which type of current we would expect to have coming out of our plugs in our houses? Can you have a go in the chat, please? So what does AC and DC stand for, and which one would we expect to see in our house? All right, okay, we've got some answers coming in. So just to make it clear, the AC and DC stand for alternating current and direct current. Which one would you expect to see in your plug? Okay, so a lot of people are saying direct current. Now, direct current is what you usually need to charge your phone, what your wires probably carry, what your device is probably working. But actually, because of the way that transformers work, we do not use direct current in the national grid, and actually it's fed into our houses as alternating current, not direct current. When you plug a charger, for example, for your phone into the socket, your phone charger then converts that alternating current into direct current. So your house, your actual mains electricity is all going to be alternating current. Does anyone know what the voltage of mains electricity is? Or have a guess if you're not sure. Right, so we got some answers coming in. It might be higher than you expect. It is indeed, and some people got this right here, 230 volts. Well done. So let's have a closer look at the differences again. Remember, for alternating current, it's literally alternating, right? So it changes direction, and for DC, it only flows in one direction. So that's what it means. So there's a diagram for direct current. It's just one line going along like that. So it's one value for the voltage. And the current time graph would be exactly the same. We just have a fixed current and it just stays constant. However, in alternating current, we have current that changes direction all the time. And as you guys said, the voltage on that would be, oh, the frequency doesn't matter too much. That's usually not tested, but the voltage is 230 volts. This number is a little bit out of whack because it's showing us the peak, but 230 volts is the correct value. Okay, well done. So that's our mains electricity, how it's generated, how it reaches our houses. Okay, now we're looking at plugs. And when we try and access electricity from our sockets into, for example, a phone charger, we need to use a plug to link the two. But let's have a closer look at plugs and their structure. So here's a diagram of the inner wirings of a plug. So let's have a little quiz. What do all the wires mean? So starting with the green one, what is the green wire? Can anyone give me a value? Sorry, can anyone name the green wire? Have a go. If you're wrong, it's not the end of the world. Okay, we've got some answers coming in. Well done, guys. So we've got someone who's just joined. Don't worry, you haven't missed too much. What we've talked about so far is just how to generate electricity, and that mains electricity is alternating current. So you're completely fine. Right now, we're trying to identify what the green wire is. So try and name the green wire. Okay, excellent. So answers are split between the earth wire and the live wire. Now, the way I always remember this is, well, green is earthy, right? We've got grass grows on the ground. So that is indeed the earth wire. Can anyone tell me what the earth wire is for? Any ideas? What is the earth wire for? Why do we need one? Can we just kick it out? Because the plug would probably still work without it. Okay, we've got some questions in. Well done, you guys. Right, okay, so well done. It is for protection. It's used for safety. Basically, if there is a short circuit or the current gets too high because of this short circuit, the earth wire is a way of directing this extra current away from whatever circuit you have. So whatever device or thing the plug is connected to, and back down into ground. So nobody gets electrocuted. That's what earth wires are for. If there's a short circuit, it will direct any excess current back down towards ground. So usually in the earth wire, we don't expect to see any current. But when there is a malfunction in the system, then that's where the current goes. So there's really only current flowing through there if something has went wrong. Right, perfect. So green, that's earth wire. The blue one, what is the blue wire? Have a go in the chat. Okay, we've got some answers coming in. Right, so we've got a lot of live wires for this one. And again, let me just explain to you how I remember this. So, okay, earth is green because the grass is green. And then how do I tell between the blue and the brown color? Well, this might be a bit grim, but the way I always learned it at GCSE is that blue is kind of a calm, neutral color. I'm thinking the sky, the sea, nothing much is going on. Whereas brown, well, brown is the color of dried blood, right? So I always imagine that live one. So if you touch it, bad things are going to happen. You're going to get hurt. So that's how I remember it. If you want to create your own system, please feel free to. But the live wire is the brown one on the right, and then the blue wire on the left is the neutral one. So we have the neutral wire. Can anyone tell me what the neutral wire is for? We've got another suggestion in the chat, which I quite like. So live is related to life. Soil is full of nutrients, so the brown is the live one. I think the danger with that is that you might confuse it with earth, but that's up to you. So remember, earth, grass is green, and the brown one, if you want to connect it to earth and it being nutrient rich and stuff, that's fine, but I'm proposing just a different one, which is less earthy. Right, the neutral wire. So we've got an answer. It's used for grounding. The earth wire sort of grounds because that one leads down to the earth. So it's not, that's not what the neutral wire is for. Any ideas what the neutral wire is there for? Any suggestions, even if you're not sure? Okay, right. So people are getting the right idea. Well done, you guys. This is to complete the circuit, the electricity path back essentially. So if we have, this is the power supply for a circuit. I know it's a cell, but let's imagine that it is actually the socket here. It's where the current will be coming back here. So this is the neutral wire. It's required to complete the circuit. So what do you think the voltage across it is? So obviously it does have current flowing through it, but what is the voltage across the neutral wire? 0, yes, well done, 0, because if you kind of imagine it, it's almost as if all the energy has already been used around the circuit. So in the neutral wire has 0 volts across it. Okay, next thing that I wanted to ask about is that little gray bit that the arrow is pointing to. What is that and what is it for? So this bit, if you can see, that's the next arrow along. So over here, what is this bit for? The bit that basically holds those 3 wires together. Right, okay, well done. So this is insulation, and what's the purpose of insulation? Why do we have insulation around those 3 wires? Right, so we've got one answer saying to stop from heating. So insulation doesn't necessarily stop from heating, but it can be negatively affected by the wires heating up. So if there is, for example, a short circuit and there's way too much current in the wires and they heat up really quickly, maybe the earth wire is not working or something, then the insulation might melt or it might catch on fire. So that's just a separate hazard. Now, someone else has put safety. And yes, exactly, it's safety. So it's basically to prevent those wires being damaged. So, you don't have a fraying live wire, which someone then touches and gets electrocuted. So yes, it's for safety, to prevent people from getting electric shocks from the wires and to prevent the wires getting damaged themselves. All right, next one is this little cover here. What do you guys think it's for? So this one's quite trivial. So the cover is just there to keep everything together, to be honest, to keep the all the wires in the plug properly to stop anything pulling. We've discussed what the brown wire is for. It is the live wire. Does anyone know what this thing over here is? It's the fuse. Well done. What's the fuse for? Right, to break the circuit. Well done. So fuses are there again. We're prepared for short circuits a lot of the time, and there's a real danger when the current gets too high in a circuit that we won't be able to, that'll lead to maybe fires, electrocution, all that bad stuff. So we include a fuse in, and as I'm seeing in the comments, well done. And the fuse wire will melt if the current is too high, so it will break the circuit and prevent these bad things from happening. Okay, so that's the fuse. And as I was saying, that was the grip. So the cable grip, that's just to hold everything together. Okay, well done, everyone. So let's look at the fuse in a little bit more detail. And I've got a bit of a fill in the gaps exercise for this. So let's read it out. We have fuses are blank devices. So pick one of the words from the bottom here. What do you think fits? Safety devices, well done. So if there is a fault in an appliance which causes so what goes in the blank there? The live and neutral or earth wire to cross. Yep, great. Then a large current will flow through the circuit, well done, and cause it to melt. Perfect. This will break the So to be honest, it could be interchangeable here. Will flow through the fuse and cause it to melt was probably the previous question. This one is, this will break the circuit for sure and protect the appliance and user from further harm. Great. So essentially what this is saying is exactly what we've just talked about. When there is a short circuit, so when the live wire and the neutral or the earth wire cross, there's some kind of malfunction, then the current gets really high, the fuse melts and the circuit is broken. Well done. All right, but there's more than one safety mechanism when it comes to breaking the circuit. There are fuses, but has anyone heard of circuit breakers? So there's a little diagram up there. Basically, the way circuit breakers work is based on electromagnets. Now, I won't go into too much detail about how electromagnets work because this isn't the lesson for it. But essentially, when the current gets too high, the electromagnet is triggered, it moves in a certain way, and therefore also breaks the circuit. So again, let's have a look at that little fill in the gap. So if the current becomes too high, which word fits in there? The electromagnet is activated. This will remember the electromagnet's acting as a magnet. So what do you think it will do to the ion? Yes, it will attract it. Well done. And the contact will be what will happen to the contact? So remember, contact is when two things touch. Right, the contact will be broken. This will break the circuit. Circuit breakers actually do have two main advantages over fuses. In fact, in most houses, we currently now have circuit breakers to protect the mains electricity rather than fuses. Okay, so the two advantages are they work. What do you think? What's the gap here? They work quicker. Excellent. They work quicker and can easily be reset. So a circuit breaker, all you need to reset it is you just flip a switch, and then that means that you're you're fit to use the circuit again. As soon as you switch it back on, it will work. A fuse, it's just melted wire, right? So you have to take that fuse out and replace it with a different one. And just a note on fuses, remember, you also have to select the right fuse for your circuit. That means you need to know your normal operational temperature of the circuit, sorry, not temperature, current of the circuit, and then just go a little bit higher. If you went lower than your operational current and your fuse, then it would just blow even when your circuit was working normally. If you go much higher than your operational temperature for your fuse, then it might not even work, or it might work a lot more slowly when there is a short circuit, and that's dangerous. All right, fab. So that's two safety mechanisms, as well as the earth wire that we use to protect ourselves from electric shocks and stuff like that. So let's do a final one on earth wires. I know we talked about this. This shouldn't be too hard. So earth wires are always used if an appliance has a, what kind of case? Right, earth wires are always used when an appliance has a metal case. Now that's super important. For example, if your toaster has a metal case, maybe some of you have that in your houses. It's safe to touch the case of the toaster, even though it's metal and it conducts. And most of the time, the reason for this is that the metal case has an earth wire attached to it. Now, if you're really silly, you might stick a fork inside your toaster while trying to get a piece of bread out. Now, this would be super dangerous because this isn't the case anymore, and you might get an electric shock if you did that, because it might not be earthed. You might actually be touching directly to the circuit. So cases usually have earth wires to prevent this kind of electrocution. Okay, if there is a blank in the appliance, what do you guys think now? What word goes here? If there is a fault in the appliance causing the live wire to touch the case. Well done. The current, we haven't talked about this word actually, but it's the current surges down the earth wire. And what do you think blows? What can we say blows? And the fuse blows. So yeah, when a fuse melts, we typically say that the fuse has blown, right? So that is the fuse that we've just seen in the plug, right? Okay, fantastic. So then let's return to the questions that we had at the beginning. So what is mains electricity and how does it get to our homes? Could you guys have a think about that now? And if you want, write out a really quick answer in the chat now that we've chatted about it. It could just be a few words that you're actually writing out, but please everyone do have a think. Right, so the answer to this one is, so electricity is produced by power stations, we discussed that, and it's transmitted at very high voltage through cables to, well, this is the national grid system, and then eventually to our homes where we see it as alternating current with a voltage of 230 volts. So the voltage that it's transmitted at is a lot higher than 230 volts, and you'll see why when you eventually do transformers. Okay. Excellent. So well done on the people that answered that. That was great. And what safety measures are used with mains electricity? So just name a list of the ones that we've looked at today. Okay, great. We've got replies pouring in. Excellent. So the main safety measures are fuses, circuit breakers, and earth cables, which are built into all of our appliances to make sure that our use of electricity is safe and we don't, electrocute ourselves or cause fires or anything like that. Right, so that was, remember the lesson today is split into two sections. The first one is in domestic uses and safety, and the second one is on static electricity. So that's us finished with the mains electricity part. Does anyone have any questions on what we've just done there? I'll wait sort of a couple of seconds just in case anyone has a question, and then we'll be moving on to our second topic today, which is static electricity. All right, well, if you do have a question, do feel free to put it in the chat and I'll just answer it as I'm going along. Okay, so we do have a question actually. Could you please explain? I'm just going to go back to the diagram on alternating and the other type of current. So as you can see on this diagram, so direct current, usually when you imagine a circuit, you think that, well, you imagine direct current, right? So you have your battery, you have your circuit, maybe it has a light bulb on it, and current only goes round in one direction, from the positive to the negative of the battery. That is because in batteries and cells, you always get direct current. Whereas in mains electricity, we would constantly be flipping the direction of the current. So it'd be going this way, and then the next second it would be going this way, and then it would change direction again. And this is shown in the diagram at the bottom there. So on the y-axis, you either have voltage or current, it doesn't matter. Negative voltage, negative current just means current and voltage in the other direction. So that's why we have that up and down graph. It's because it's constantly switching direction. I know that this might be a bit weird to think about, given that you're used to circuits with batteries and therefore you only have direct current, but so why is it switching direction? This is a good question. And in answer to that, I would probably direct you in the direction of the electromagnetism topic. Essentially, the reason why it's switching direction is because it's generated like this. So when we turn the turbine and then we use the generator to generate electricity, what we're actually doing is moving conductors, moving wires through magnetic fields. And that moves one way, but then it moves the other way, and then it moves one way, and then it moves the other way. It goes in like a loop. So when it's moving one way, current is positive. When it's moving the other way, current is negative. So we get this natural sort of loop because your turbine is turning, and that is reflected in our alternating current. So because this current comes straight from the power stations via a system of cables, and that is what we get out of our sockets. We get alternating current. And then our chargers, devices, everything like that, we then have to turn it into direct current. I hope I've answered your question. Does that make sense now? Okay, great. So if you want to know a bit more about it, definitely have a look at the electromagnetism topic and pay attention when you're learning about generators, dynamos, stuff like that. Right, so to go back to, if anyone has any other questions, by the way, please feel free to ask them. Right, so we have then moving on to static electricity. I've got a few questions for you to think about here. So what is the structure of an atom and what are the particles in an atom? Can anyone tell me what are the particles in an atom? 3 of them. Which 3 particles are we thinking of? Right, we've got, obviously, we've been learning this sort of year 9, maybe even before that. We've got protons, neutrons, and electrons. And which of those have a positive charge? Protons. And which of those have a negative charge? Excellent, electrons. Now, usually, okay, so all materials are made out of atoms. We know that again. And usually atoms, neutral atoms, have an equal number of negative and positive charges. So they have an equal number of electrons and protons. But what happens when you knock, electrons off and you change the structure of the atom? So when we form a negative ion, we gain an electron in there, and when we form a positive ion, we lose an electron here. So yeah, you become positive. So as you can see, this is only possible with the movement of electrons. It's really important to remember that protons don't move at all. Atoms stay where we've put them. Atoms stick in that material. You can't just transfer, ions or atoms from one material to the other, but electron transfer is completely possible. So electrons like to move around, and that means that we have a really interesting phenomena called static electricity. So has anyone ever, put maybe a wool jumper on, there's friction everywhere, you're rubbing it against maybe the t-shirt that you've got underneath, and then you've touched maybe a metal railing. Can someone tell me what happens when you do that? What happens when you touch a metal railing? Right, you get a little electric shock, right? You get a little buzz and you maybe yank your hand away. Now, why does that happen? Can anyone give me any ideas? Why does that happen? So why have we suddenly got an electric shock with our metal railing after we've put a jumper on? What's changed? Right, so people are putting in the chat that this is due to static electricity, and indeed it is. So static electricity is the process of transferring electrons from one material, usually one insulator, to the other. So here's a little sort of animation. Let me just play it again for those of you who didn't see. So when you rub 2 objects together, you might transfer charges from one material to the other. So here, the light blue ball was rubbed against the dark blue object, and it transferred negative electrons from the light blue ball to the dark blue ball. So what overall charge would the light blue ball have here? It has a positive charge. Excellent. And what charge would the dark blue object have? Negative. Yes, well done. So in essence, that's what's happening with you and the jumper. So when the jumper rubs against you, it's either transferring electrons towards you or you're transferring electrons to it, because you're both insulators, and when 2 insulators rub together, they can transfer electrons and cause a concentration of charge on them. So where there's a lack of electrons, it's positive. Where there's more electrons, then it's negative. Now, when you then touch the railing, that X charge so the electrons jump onto the railing, that causes a little bit of a current, you experience an electric shock, or you're slightly positively charged and the railing transfers electrons to you, again causing a little bit of a current and a little bit of an electric shock. So that's that's discharge of the static electricity. But what happens when you're still charged? Well, okay, so this is usually and someone I think mentioned it in the chat, usually the comparisons that are made with static electricity are rubbing a rod and a cloth together. So one of them is going to come away positive, one of them is going to come away negative, or maybe your hair and a balloon, if anyone's done that experiment. So you're rubbing your hair with a balloon, and then one of them becomes positively charged, one becomes negatively charged. So after you rub your hair with the balloon, what happens? What can you see? Why do people do this? It's a bit of a weird thing to do. What are you expecting? Right, so people are putting in the chat that it sticks, right? The hair sticks to the balloon, great. And this is because of this transfer of charge. So my hair, for example, might be negative, my balloon might be positive. And remember that opposites attract, therefore they're going to be attracted to each other because one of them has transferred electrons to the other, and therefore there's this buildup of charge due to friction. So it's really important that you remember the reason that the electrons are being transferred is because of the effect of friction. So can anyone tell me, for example, what would be the result if I, rubbed a rod and a cloth together, and then I held them like this? What would I expect to see? Any ideas? I would expect to see attraction. Yeah, I would expect them to be attracted to each other. Great. And just a note is that you can never really predict which one has the electrons transferred to it and which one basically is transferring the electrons away from it. It depends on the materials, and you'll never be asked to predict that. Whenever you have a question which seems to be asking, just guess one, and the marks team will have both answers available, because at GCSE level you really don't need to worry about that. So yeah, as I said, it could happen the other way. This depends on the material. So if you rub that again, you can actually have the electrons transferred to the light blue ball here. It doesn't matter, just write about one of them and you'll get it right. So this time the electrons have been rubbed off the rod and onto the cloth. The rod is positive and the cloth is negative. So again, let's have a look at these two diagrams. The left-hand side object, is the overall charge there positive or negative? Right, so we've got some answers. We've got negative, yep, and the right-hand side one. Right, positive. Okay, so I did mention just in my explanation a little bit about how this only works if you have two insulators. Do you guys have any idea why this only works with insulators? So remember, what's an insulator? An insulator is something that does not conduct electricity. Why does this only work with insulators? Just put your ideas down and we'll talk about it in just a minute. Go on, give it a go. So we've got a question there, and this is an interesting question. So, won't insulators prevent the transfer of electrons? So, insulators are materials in which electrons can't flow freely throughout the structure. They can't move throughout it. So, insulators won't actually prevent the transfer of electrons from material to material, but once they're in that material, electrons won't be able to flow freely around it. The reason you can't charge a conductor up with static electricity is because once you have a small concentration of these electrons, because static electricity usually only acts on a small level. So you rub together the rod and the cloth, you have one area of the rod which is a bit positive, let's say. With a conductor, those electrons that you've transferred to the cloth would be moving around all over the place. They wouldn't stick to the area that you've got them in. So in both of those diagrams, can you see how the charge is concentrated on the right-hand side of the object? And that is because it's probably been rubbed there. In a conductor, this charge would disperse amongst the entire conductor, so you wouldn't have a concentration of electrons and therefore negative charge anywhere. You would just have all the electrons whizzing around, and really the effect of the charge will be negligible. Does everyone understand that? Or is there any questions about why insulators can be charged up, but conductors can't? If you have any questions, please drop them, and I will come back to them. Right. And again, focusing on the second idea that opposite charges attract, like charges repel. I mean, you've heard this from probably primary school, right? A positive and a positive charge. You can't really force them together. It's really hard to do. So they repel each other. A positive and a negative charge, they attract each other. So that's what's happening with the rod and the cloth. Obviously, they're oppositely charged, so they will attract each other. So we've got to, these two objects attract. We've got a positive and a negative here. These ones attract, it's reversed. These ones repel because they're both like charges, and these ones repel as well. So yeah, and remember that this charging up, this does not work like a magnet. There's not an area of negative charge on the other side and like positive charge on one side, because we only have that concentration of electrons or lack of electrons in one area. So we don't just have a corresponding concentration of electrons on the other side. So try not to get them confused with actually working like magnets, because they're not quite. All right, perfect. So just for these two, obviously the top one, what will happen to the top one? Okay, it repels, and the bottom one, well, the bottom one is opposite charges, so it will attract. Perfect. Okay, I've got a little bit of an exercise for you there. So have a read through these statements, and can you please tell me what is true? So a plastic ruler is rubbed on a duster, the ruler becomes negatively charged, and just write the number of the statement that is true. So 1, 2, 3, 4, or 5. Which one is, which two of those are true? So I'll give you a minute for that. Okay, we've got some answers. Well done. The correct answers are 3 and 4, because we know that the ruler is negatively charged, therefore it must have gained electrons, and we know that the duster is where those electrons came from, so the duster must have lost electrons. So 3 and 4. Well done, you guys. Okay, let's have a talk about something slightly different now. So another experiment for static electricity is, okay, I rub the rod and the cloth together, but then I take the rod and I put it in some bits of paper. The bits of paper, even though I've done absolutely nothing to them, so tiny little bits of paper, they stick to the rod. Why do you think that is? Does anyone have any ideas? Pop them in the chat. So it is because the paper is uncharged, but that's not the full explanation. So the paper is not negatively charged. It does not start off negatively charged. That little title, I'm going to go into a bit of detail afterwards. But yep, the paper is uncharged, but it's still attracted to the rod. Okay, well, let's have a look at a diagram of this, shall we? So this is a model in which it's slightly different, but essentially you rub the balloon again. Some of you may have done this, right? You rub the balloon against your head again. And so it's charged up, all that friction, it's got electrons on the balloon this time. And then you take it and you stick it to a wall. You let go and it sticks. The balloon sticks by itself. So if you haven't tried it yet, I do advise it. It actually does work. And we say that, okay, so which is positive? Obviously, my head is positive, the balloon is negatively charged, because it's got electrons transferred to it. And we see that the hair is left with fewer electrons. Remember, it always describes stuff in terms of electrons. It doesn't have more positive charges, it just has fewer negative ones, and therefore the balloon is negative. Okay. So what's actually happening when it sticks to the wall? Remember that electrons can exert, forces of repulsion, attraction. When the balloon moves to the wall, what's happening is that the negative charges, i.e. the electrons in the wall, are repelled by that concentration of negative charge in the balloon. So when I bring my balloon to the wall, the electrons in this side of the balloon are repelling any electrons in the wall, and therefore I have what's called an induced charge. I have induced a charge, that means caused a charge in my wall, because I've shoved the electrons away, and now I have an area of positive charge, which means therefore the balloon and the wall attract each other. The way to explain this really concisely for exams or something is to say the negative electrons in the balloon repel the negative electrons in the wall. Therefore, there is an induced positive charge in the wall. Opposite charges attract, so the balloon and the wall stick to each other. Okay, so and summarized, there's that on the slide as well. So positive and negative, positives and negatives are together because all of these negatives have been repelled by the balloon, and therefore the balloon sticks to the wall. Okay, great. So if the balloon is positive, how does it stick? So we're repeating the same experiment, but with a bit of a different setup. This time, when I rub my balloon against my head, the electrons travel onto my hair. So the balloon is positive. Does anyone have any ideas why does it still stick if my balloon is positive? Can you type it out in the chat? Any suggestions are welcome. It could just be a little sentence answer. Don't worry if it's wrong. Does anyone have any ideas? Go on, so summarize it quickly. In my first example, the balloon induced a positive charge in the wall by repelling electrons in the wall. What do you think is happening here? Okay, so some ideas. Essentially, the reverse is happening. So when the balloon is brought closer to the wall, now I just want you to be really, really careful because some of the answers here mentioned protons. Remember what we said? Protons don't move. Protons are not all we're talking about here. I know that protons are charged particles, but protons stick where we tell them to be. They stay on the material, and yeah, don't worry about it. Loads of people make this mistake. Good that you brought it up, actually. So we only talk about electrons moving when we talk about, static electricity, etc. So in this case, I know only the positive charge is marked on the balloon. That might be a bit jarring, but essentially it just means a lack of electrons, right? So this positively charged balloon moves close to the wall surface, and now the electrons in the wall are attracted to this positive balloon, right? So instead of a negative induced charge, we have a positive induced charge in the wall. We have a negative induced charge in the wall, with all the electrons being brought forward towards the balloon, and therefore there is attraction. So the negatives are attracted towards the wall nearest the balloon. And we have negative charges going over here. And again, opposite charges attract. So the balloon still sticks to the wall, even if it is positive. Great. What else attracts? Well, we could have a charged object next to a stream of water. If we have a rod that we've charged up, we bring it next to a stream of water. Water molecules are actually charged, kind of. They have negative bits and positive bits. So you can repel a stream of water with a charged object via static electricity. Again, the picking up tissues example is what I used at the beginning. So a comb, which is negatively charged, would repel the electrons in the tissue paper, and then causing a induced positive charge in the tissue paper, which you can then use the comb to pick up the tissue paper with. This is a super fun experiment to try. It does definitely work. You just need a cloth, a comb, which I'm sure most of you have just lying around your house, and you can pick up bits of ripped up tissue paper. All right. Right. So again, I've got a little bit of a practice question for you guys to try. So can you put the sentences in order? Have a read through this equipment. I know this is new to you, so some of these just require you to figure out what's happening here. So I want you to put the sentences in order. So currently they're 1, 2, 3, 4. Which order would they go in to describe how the electroscope works? Oops, that was not what I wanted. There we go. Right, so we've got some answers in the chat. Okay, well done. The correct answer for these, yes, is 4, 1, 2, 3. I've lost my mouse, which is why I'm messing up the PowerPoint a little bit here. So let me just see if I can fix that. There we go, sorry. So 4, 1, 2, 3, excellent. So the object is brought near the plate, the electrons move to the metal plate, and therefore the gold leaves has a positive charge. The gold leaves repel each other. Well done. All right. Let's have a look at some of the other uses of static electricity then. So we have firstly an inkjet printer. In an inkjet printer, you have droplets of ink which are charged. They're passed between two metal plates. One of them has positive charge, one of them has negative charge, and the droplets are attracted to the plate with the opposite charge. So here we have a diagram of this working, and essentially you then end up with an image. So there's basically two models. In an inkjet printer, you end up with directing the ink. In the little diagram I've got here, there's a different model in which you basically have the same charged ink droplets, but instead of attracting them to a particular plate, you shine light on the material. It makes the charge disappear of some of the ink droplets, and then only some of them are attracted to the paper. So you can use them in photocopiers and inkjet printers. Okay. However, there are also some dangers when we think about static electricity. So, yeah, okay. When we are refueling tankers or aircraft, places where we have massive amounts of fuel, we have loads of stuff which is very flammable, right? So when we think about the electric shock that we get from touching a metal railing, that's just uncomfortable, but it's not a really big problem. But when we have a tanker or an aircraft that we're refueling, this will be a massive problem, because even if we have a small spark, fuel is very flammable. So if we ignite the fuel with that spark, we can cause a fire or an explosion. If there's loads of fuel in one place, and this explosion might be really terrible. So here we have a fuel line in my picture going to an aircraft. There might be static electricity when you're refueling, so any kind of friction, and therefore it might be that the fuel catches fire and explodes. Does anyone have any idea how to prevent that? How do we prevent the negative effect of static electricity? How do we prevent the charge from building up? Any ideas? Right, great. So we've got some people suggesting puts an earth wire. Exactly right. Remember, earth wires take excess charge down to earth. So if we have an earth wire on that fuel line, the electrostatic charge will never build up, and we will never have this spark causing the ignition. So fuel lines always have earth wires connected to them. So we never have this buildup of static electricity. Okay, so we've already talked about this a bit actually. Obviously, static buildup of static electricity, static charge can also result in an electric shock. If we don't just have our jumper being put on, which is a very small buildup of charge, but we have a massive, pipe or anything that's having a lot of friction on it, that might be a large buildup of static electricity and charge, and therefore the electric shock might be bigger. But as you've just said, earthing offers electrons an alternative pathway to Earth. So this prevents too much electrostatic charge from building up and reduces the risk of an electric shock. So again, we've got a solution as just earthing whatever substance that we have with the static electricity and charge building up. All right, finally, we've got this example. So electrostatic charge can build up on clouds due to friction. This little animation is just showing you how a lightning bolt happens. So electrostatic charge building up on the clouds. We've got those negative charges, and then eventually even though air is usually an insulator, eventually that charge builds up so much that you have a spark, and therefore you have a lightning bolt striking the ground. And again, this is really dangerous, and you can't really earth the clouds, right? So instead, what they do in situations like these is just basically divert the lightning, so make it more likely to strike in a particular place. So they have essentially like lightning attractor rods, which means that their lightning is more likely to hit them than it is to hit, a human who's out in the open. All right, so obviously lightning is another danger of static electricity, and that's why lightning happens. Right, so just to finish off the lesson, then I've got a couple of questions about static electricity. So let's have a look at question 1, read through the question, and then once you're ready, can you tell me which of the answers is correct, A, B, C, or D? which answer do you guys think is correct? A, B, C, or D after reading through the question? Have a go. Anyone got ideas? We've got a couple of answers. Keep them coming in. Right, so we've got two things to consider here. We've got to, whether the charge is positive or negative and whether the size of the charge is equal or bigger. Well, the plastic rod becomes negatively charged, so that means we've transferred electrons to it. So that means that the cloth must have lost electrons, so it must be positive. So now we're narrowed down to A or C. Now, considering the size of the charge, remember that electrons, if you transfer them from one object to the other, that creates a positive charge of the same size as the negative charge we have in the negatively charged object. So the size of the charge would be equal. So your correct answer here is A. Right, and then finally, part 2. Can you write out a sentence, including the buzzwords that we've talked about today, that explains how the plastic rod becomes negatively charged? So think about where the 2 marks could be, and I'll give you a minute just to write that out in the chat, and then I'll go through what usually the marking points will be for these kind of questions. So do have a go, see if you would get those 2 marks. Right, so we've got a couple of ideas, and I just wanted to firstly go through what the marks you would probably expect. So as I mentioned, it's very important to mention that it's via friction. So via friction, electrons get transferred from the cloth to the plastic rod. So it's important to tell us which direction the electrons are getting transferred. So well done, many of you got that, causing the rods to become negatively charged, the cloth to become positively charged. So you mentioned that it's via friction, mentioned the correct direction which the electrons are going. Just one thing to be careful from some of your answers is that you're not talking about just one electron being transferred. I know in a lot of my diagrams, I may have made it seem as if we just have one electron and that's going to cause some kind of brand effect. I just couldn't be bothered to draw out many pluses and minuses, if I'm honest. The main thing is that this is happening with multiple electrons. So electrons are transferred from one to the other, and therefore we see that effect of static electricity with charge building up. So if it was just one electron, we wouldn't really have a noticeable effect. But when charge builds up, it's usually a lot of electrons, especially when we have effect such as lightning from clouds. That comes from tons of charge building up, and why we see such impressive sparks. Right, everyone, so that is the end of today's lecture. I am just going to stick around for a couple of minutes to answer any questions if you have it. And just like to remind everyone that next week I'm going to be covering the topic of electrical energy transfers. So thinking about different components, linking that back to your energy topics if you've covered that. Usually it's the first topic that you cover in year 10. Same time next week I will be here. So if anyone has any questions, please do put them in the chat. And I'll just wait a minute if anyone's typing anything out. Nope, no one. Okay, no problem. I hope you all found that interesting and informative. And I hope to see a lot of you next week. Thank you. Bye.